So hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question number 1 is to write the Lewis structure of sulfur tetrafluoride. So when we write the Lewis structure, we first want to find out the total valence electrons in the molecule. So total valence electrons, and for sulfur, this is equal to 6. And in the case of a fluorine atom, this is equal to 7. And since we have 4 of them, this gives us 28. And then let's add up the total valence electrons, which is 34. Okay, so now let's draw sulfur as our central atom. And we'll draw each of the fluorines just attached with a double bond. And now let's show all of the lone pairs on all of the terminal atoms as well. And then after this step, I like to count out how many I've drawn so far. So we need 34 valence electrons in total. And if we recall that each bond contains 2 bonding electrons, and we have 4 bonds, so this is 8. And then we're going to add all of the lone pairs involved as well. So each terminal atom has 6 times 4, so that's 24 plus 8, which is 32. So all we need to draw are 2 more electrons, and I'll draw them on the sulfur atom so that the Lewis structure now looks like this. Okay, so this is correct, and let's see what the junior tutor said. When writing Lewis structures, the total number of electrons that need to be distributed is counted first by adding the valence electrons of each individual atom. If a formal charge is present on the molecule, this is also taken into account in the total number of electrons. Skeletal structure is first written by distributing bonding electron pairs. Then the lone pairs are distributed until the octet is completed. Formal charges are added to the atom if the number of electrons does not satisfy the octet to indicate that an electron has been transferred, added, or removed. Structure with the least number of formal charges or have the smaller charge is the most stable Lewis structure. Sulfur tetrafluoride has a total of 34 valence electrons. 8 are in 4 bonding pairs, with the fluorine atoms around the central sulfur. The remaining 26 are distributed in lone pairs, 3 of each for the 4 fluorine atoms and the 2 remaining on the sulfur. Great, so this solution is correct. Okay, so question 2 is to draw the Lewis structure for ethylene. And ethylene is C2H4. So first, let's find out the total valence electrons for this molecule. So for carbon atom has 4 valence electrons, and there are 2 of them. So this is 8. And for hydrogen, each hydrogen atom has one valence electron. There's also 2 of them. This is 2. If we add them all up, we have a total of 10 valence electrons. So now let's draw our 2 carbons, single bonded. And then we'll try to draw symmetrically our 4 hydrogen atoms. And now let's stop to see how many electrons are in this structure. So if we recall that each bond has 2 electrons participating, and we have 5 bonds, this is 10 electrons, so we already have our 10 electrons. But if we look at our carbons, you'll notice that they don't have a full octet yet. So we'll draw a double bond in between the 2. And this is the structure for ethylene. Okay, so let's see what the junior tutor said. When drawing Lewis structures, the total number of electrons that needs to be distributed is counted first by adding the valence electrons of each individual atom. If a formal charge is present on the molecule, this is also taken into account in the total number of electrons. A skeletal structure is written first by distributing bonding electron pairs. Then the lone pairs are distributed until the octet is completed. Formal charges are added to the atom if the number of electrons does not satisfy the octet to indicate that an electron has been transferred, added, or removed. Structure with the least number of formal charges or has the smaller charge is the most stable Lewis structure. Okay, so let's see the Lewis structure that they have. We have the carbons that now have a full octet with a single double bond. And all of the hydrogens are attached as single bonds. So this solution is correct. I think I see a mistake I did where there are 4 hydrogen atoms instead of the 2. So this is why we have an extra pair. So 1 electron times 4. So our total valence electrons should be 12. So that's why there is now a double bond, because not only did the carbons not have a full octet, we also only had the 10 electrons drawn. So this is the correct Lewis structure for ethylene. Okay, so question number 3 is to draw the Lewis structure of xenon difluoride. Okay, so first let's find out the total valence electrons for this molecule. Xenon has 8, and fluorine has 7, and there are 2 fluorine atoms. So 14 plus 8 is 22. So now let's draw our xenon in the middle and our 2 fluorine atoms on either side. And we'll draw out all the lone pairs on the terminal fluorine atoms first. And if we count out how many electrons I've drawn so far, let's recall that each bond contains 2 electrons. So far I have drawn 1, 2, 3, 4, 5, 6, 7, 8 times 2, so 16. But I need 22 more, so I'm going to draw the remaining 6 as lone pairs on the xenon. So xenon is one of the exceptions to the octet rule, in which it is able to have more than 8 shared electrons in its valence shell. And if we see what the junior tutor said, when drawing Lewis structures, the total number of electrons that need to be distributed is counted first by adding the valence electrons of each individual atom. If a formal charge is present on the molecule, this is also taken into account in the total number of electrons. A skeletal structure is first written by distributing bonding electron pairs. Then the lone pairs are distributed until the octet is completed. So xenon difluoride has 22, and they got the following Lewis structure, which is correct. Okay, so question number 4 is to just draw Lewis structures for the following molecules. So first we have sulfur hexafluoride. Let's calculate the total valence electrons in this molecule. So sulfur has 6 and fluorine has 7, but there are 6 fluorine atoms in total. So if we added it all up, we get a total of 48 valence electrons. So now let's just draw sulfur as our central atom, and then the 6 fluorines arranged as symmetrically as I can. And now I'm just going to show all of the lone pairs on the terminal fluorine atoms. So if we recall that each bond contains 2 electrons, and we have a total of 6 bonds, that is 12 so far. And then each fluorine atom has 6 electrons in the form of lone pairs. So 6 times 6 is 36, plus 12 is 48. So this is the following Lewis structure for sulfur hexafluoride. Okay, so now let's do the next molecule, aluminum fluoride. The total valence electrons are the following, where aluminum has 3 and chlorine has 7, but there are 3 chlorine atoms, so we have a total of 24. Okay, so now let's draw aluminum as our central atom and the 3 chlorine atoms around it, showing all of their lone pairs. If we were to count out how many electrons I've drawn so far, 2 in each bond, this is already 24, so we don't need to add any additional lone pairs on aluminum. And that is the following Lewis structure. Okay, so let's try to fit carbon disulfide, the bottom here. For the total valence electrons, carbon has 4, sulfur has 6 times 2, which is 12. So we have a total of 16 valence electrons in carbon disulfide. So now let's draw carbon as our central atom, single bonded to the 2 sulfurs. So I've only drawn 4 electrons so far because I have 2 bonds, but I'll draw them as double bonds just so that carbon can have a full octet, and we can draw the remaining on the sulfur, and then this should give us 16 valence electrons. Everything has a full octet, so that is correct. Then I'll try to fit the remaining Lewis structures on the next page. For D, we have selenium bonded with 4 fluorines. So selenium has 6 valence electrons, and each fluorine atom has 7, and there are 4 of them in total. So 28 plus 6 is 34. So let's draw selenium as our central atom, and the 4 fluorines all around, showing all of their lone pairs. And if we counted it out so far, we have 4 bonds to the fluorine, so 8 times 4, so we have 32 drawn so far. So for the last 2 electrons, I'll add them as lone pairs on selenium. Okay, so now let's move on to E. We have beryllium bonded with 2 chlorine atoms. And note this molecule does not follow the octet rule, so this is helpful for us. So beryllium has 2 valence electrons. Each chlorine atom has 7 times 2, so we need 16. Let's draw beryllium as our central atom, and the 2 chlorines on either side. And we'll just show all the lone pairs on chlorine. And if we added up all the electrons so far, we now have 16. So beryllium, again, is an exception to the octet rule, so this would be our correct structure, Lewis structure for beryllium dichloride. And now let's do the last molecule. So dinitrogen tetraoxide. So nitrogen has 5 valence electrons times 2, 10. Oxygen has 6 times 4 is 24. So in total, we have 34 valence electrons in this molecule. So now let's draw the 2 nitrogens together, and then we'll symmetrically try to draw all the oxygens single bonded. So now notice that the 2 nitrogens in the middle don't yet have a full octet. So I'll draw each one as a double bond. And let's see how many electrons we've drawn if I just fill in the remaining electrons. So far we have 7 bonds, and we have, let me count out all the electrons we have drawn so far. So we have 34 already, and if we were to show all of the charges, the 2 nitrogens would have the positive charge, which is good since nitrogen is the less electronegative than the oxygen, which should hold the 2 negative charges So now that all the charges cancel each other out, we have a neutral molecule. So this is the following Lewis structure for dinitrogen tetraoxide. Okay, so let's see what the junior tutor said, starting with our first molecule. When drawing Lewis structures, the total number of electrons that need to be distributed is counted first by adding the valence electrons of each individual atom. If a formal charge is present on the molecule, this is also taken into account in the total number of electrons. The skeletal structure is first written by distributing bonding electron pairs. Then the lone pairs are distributed until the octet is completed. Formal charges are added to the atom if the number of electrons does not satisfy the octet to indicate that an electron has been transferred, added, or removed. Structure with the least number of formal charges or has the smaller charge is the most stable. For sulfur hexafluoride, they have the same Lewis structure, is correct. For aluminum chloride, there are 24 valence electrons and got the same Lewis structure as well. Carbon disulfide, you see that the carbon has the 2 double bonds. This is correct. Selenium tetrafluoride has 34. So this is correct as well. Beryllium chloride has 16 and doesn't follow the octet rule, so this is correct. Dinitrogen tetroxide has 14 in the bond pairs and 4 pairs are in 2 double bonds. Yep. And then they show how the charges would cancel each other out. So this is correct as well. So this solution is correct. Okay, so question number 5 asks, what is the electron configuration for sulfur? Okay, so I'll just quickly explain how one can find the electron configuration. So the first step is to draw out, well, not draw out, but to section off your periodic table into the different orbitals. So this is an example of what that would look like. So the 2 leftmost columns is the S block, and this green like rectangle from 5 to 10 is the P block, and the middle transition metals is the D block, and the last 2 rows, which are the lactanides and actinides, is the F block. So when we want to write out the electron configuration, we would first start off at hydrogen and then move left to right across the periodic table until we get to our desired element, which is the sulfur. So we would write the row number and then the block letter and then show how many electrons would be in that orbital. So starting at hydrogen, we have 1s, then going across is 1s2, and then onto the next row with the lithium and beryllium, we have 2s2, and then going across to 2p, we have 2p6, and then onto the next row, which is 3s2, and then skip over to 3p, and then to get to sulfur, we just need to count up to it. So 1, 2, 3, 4. So this is the following electron configuration, and we can also write this in the shorthand way. And to do that, you just need to look at the noble gas that comes before sulfur, which is neon. So we just put that in square brackets. And then we just continue on naming the rest of the electron configuration normally. So neon 3s2, 3p4. Okay, so let's see what the junior tutor said. Neon 3s2, 3p4. Explanation. They went all out with the explanation to an element's electron configuration is a numeric representation of its electron orbitals. Electron orbitals are regions around an atom's nucleus where electrons are likely to be located. An electron configuration can tell a reader how many electron orbitals an atom has, as well as the number of electrons in each of its orbitals. So it shows the distribution of electrons of an atom in a molecule. Area where the electrons orbit is called an electron shell. As an atom or molecule gains electrons, they fill different orbital sets according to a specific order. Each set of orbitals contains an even number of electrons when full. The sets of orbitals are the s orbital, which can hold 2, the p orbital that can hold 6, the d orbital can hold 10 electrons, and the f orbital can hold 14. So when writing electron configuration, find the element's atomic number and locate it on the periodic table. Determine the atom's charge. Uncharged atoms will have exactly the number of electrons as represented by the atomic number. The electron configuration notation, so there clearly displays the number of electrons in an atom as well as the number of electrons in each orbital. So they should be written in sequence. Number of electrons written in the superscript to the orbital name. And the final electron configuration is a string of orbital names and superscripts. Fill in the orbitals according to the number of electrons in the atom. And they show how when you write electron configuration, fill in the electron orbitals starting with the lowest energy, following the Aufbau principle, Pauli exclusion principle, and Hund's rule. And they got the correct answer. Yeah, so this solution is correct. They had a very in-depth and well-explained answer. Okay, so question number 7. Is the carbon-hydrogen bond in CH4 polar or nonpolar? What about the CH4 molecule as a whole? Is it polar or nonpolar? So let's draw out methane, which is CH4. And the first part of the question asks if the carbon-hydrogen bond is polar or nonpolar. So to do that, we need to find the difference in electronegativity for both carbon and hydrogen. So let's look up the electronegativity values for these two elements. So carbon has an electronegativity value of 2.5. And hydrogen is 2.1. So for their difference in electronegativity, it's only 0.4. So since the difference in electronegativity is less than 0.5, then this means that the carbon-hydrogen bond is nonpolar. So that means that since carbon has a similar electronegativity with hydrogen, there's not really like a dipole moment that is being formed between the two, like they're kind of just equal. So the second part of the question asks if the molecule as a whole is polar or nonpolar. So not only is this molecule fully like symmetrical in a sense that if there was dipole moments that were being formed, they would all cancel each other out anyways. So not only is it symmetrical, they also only contain nonpolar bonds. So therefore the CH4 molecule is also nonpolar. Okay, so let's see what the junior tutor said. Bond type can be predicted by the difference in electronegativity of the two atoms. As a rule of thumb, the bond is purely covalent if the electronegativity difference is below 0.4. In the Pauling scales, carbon has an electronegativity value of 2.55 and hydrogen has a value of 2.2. So the electronegativity difference is 0.35. Therefore, the carbon-hydrogen bond is considered purely covalent and nonpolar. Since the molecule is composed of carbon-hydrogen bonds, then the molecule as a whole is also not polar. Okay, so this solution is correct. Okay, so question 8. Draw the Lewis dot structure for CH2Cl2. So this is also known as dichloromethane. Okay, so first let's find the total valence electrons for dichloromethane. We have carbon, which has 4 valence electrons, hydrogen, which has 1, and there are 2 hydrogen atoms, and then lastly, chlorine has 7, and there are also 2 chlorine atoms, so we multiply those by 2, and if we add it all up, we have 4 plus 2, which is 6, plus 14, so there are 20 electrons in dichloromethane. So now let's draw carbon as our central atom, and then we'll show all of the other atoms as single bonds. And then I'll just fill in all the lone pairs that would be on chlorine. And in the case of hydrogen, there would be no lone pairs, since hydrogen only has the 1 electron in its valence shell. So it can only be used in the single bond. So now let's count out how many electrons I've drawn so far. If we recall that each bond contains 2 shared electrons, so we have 4 bonds, so we have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have already drawn our 20 electrons. And for the second part of the question, is this molecule polar? So first, let's recall that chlorine is much more electronegative than carbon. So dipole moments will be formed and there'll be electrons are being pulled more in the direction of the chlorine atoms. So also notice that because of this pull, we have a net dipole moment going towards direction where the chlorine atoms are located. So because of this, this molecule is polar. If the 2 hydrogens were also chlorine atoms, then all the bonds would cancel out and you would get a nonpolar molecule. But since the two hydrogens are not electronegative enough to cancel out these chlorines, this is why the molecule as a whole is polar. And now let's see what the junior tutor said. Lewis structure is this, which is the same. DCM, dichloromethane, is a polar molecule. It has a tetrahedral molecular geometry, so the net dipole moment in the carbon-chlorine bonds, which is greater than that of the carbon-hydrogen bonds, is not cancelled out. The chlorine end, which has a greater electronegativity, has a slightly negative charge, while the carbon and hydrogen end has a slightly positive charge. So we can show that on the molecule, how the side that has the two chlorines is partially negative, and the side with the two hydrogens is partially positive. So this solution is correct. Okay, so question number 9 is to draw the Lewis structure for chloroform, CHCl3. What are its electron pair and molecular geometries? What orbitals on carbon, hydrogen, and chlorine overlap to form bonds involving these elements? So we have chloroform, CHCl3. So first we need to write its Lewis structure, so let's find the total valence electrons in this molecule. So carbon has 4, hydrogen has 1, and a chlorine atom has 7, and there are 3 of them. So we multiply 7 by 3, and we get a total of 26 valence electrons in the molecule. So now let's draw carbon as our central atom. We'll draw single bonds to all of the terminal atoms as well. And I'll show all of the lone pairs on chlorine. So now let's count out all the electrons I've drawn so far. So each bond contains 2 shared electrons, and we have 4 bonds, so that's 8. And then each chlorine has 6 valence electrons. So 6 times 3 is 24. I have a mind. Yeah, 6 times 3 is 18. So we have a total of 26 electrons in this structure. So the second part of the question is, what are its electron pair and molecular geometries? So if we look at this chloroform molecule, we'll see that our central atom, which is carbon, has 0 lone pairs, and it has 4 bonding pairs, or bonding groups. You can also call them charge clouds. So it only has 4 of these bonding pairs. So now let's look at a helpful Vesper table and try to locate the structure of this molecule on the table. So when you have 0 lone pairs and 4 bonded atoms, this is a tetrahedral. So this is shown right here. So both the molecular shape and electron geometry is tetrahedral. And in terms of its hybridization, this is known as an sp3 hybridization. And the bond angles in between each atom is 109.5 degrees. So the next part of the question asks, what orbitals on carbon, hydrogen, and chlorine overlap to form bonds involving these elements? So if we look at the atoms that are given, then we have 3 hybrid orbitals overlap with singly occupied p orbitals of the chlorine atoms. And this forms a sigma bond. So sigma is this symbol right there, sigma bond. And we also have a last hybrid orbital with the hydrogen, so last hybrid orbital overlaps with a singly occupied (1s) orbital. So this is the hydrogen bond to form another sigma bond. Okay, so let's see what the junior tutor said. Lewis structure for chloroform is shown below, so yep, this is correct. It has both tetrahedral molecular geometry and electron pair geometry. Carbon and chlorine atoms are sp3 hybridized. One of 4 sp3 orbitals of carbon overlaps with the 1s orbital of hydrogen to form a sigma bond. The remaining sp3 orbitals of carbon overlap with the sp3 orbitals of chlorine to form 3 separate sigma bonds. The rest of the sp3 orbitals of the chlorine atoms contain the lone electron pairs. Yep, so this solution is correct. Okay, so question 10 is to draw the Lewis structures of N2H4, N2H2, and N2. Let's start with the dinitrogen tetrahydride and find out the total valence electrons for this molecule. So nitrogen has 5, and there are 2 of them. Hydrogen has 1, and there are 4 of them. So 10 plus 4, 14. And now let's draw our nitrogens bonded together. And then symmetrically all around it, I'll draw the 4 hydrogen atoms. And notice that if we count out how many electrons I've drawn so far, each bond contains 2 electrons. So we only have 10 so far in this structure. So for the remaining 4 electrons, I'm going to add lone pairs on the 2 hydrogen atoms. Okay, so this is the Lewis structure of N2H4. So now for N2H2. Total valence electrons for nitrogen is 10 again. And for hydrogen, there's only 2 hydrogens. So we only have 12 electrons in this structure. So let's draw the 2 nitrogens again and show the 2 hydrogens. And notice that the nitrogens don't have a full octet yet. So we'll draw a double bond between the 2. And for the last 4 electrons that needs to be drawn, I'll show them as lone pairs. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons for this molecule. and everything is just neutral. And lastly, for just diatomic nitrogen, N2, its total valence electrons is just 5 times 2, which is 10. So in this case, we just have the two nitrogens that will have a triple bond, and both will have a lone pair. So this gives us 10 electrons in total, and these are the 3 Lewis structures. So if we see what the junior tutor said, N2H4, yep, N2H2, and N2. So this solution is correct. Okay, so question 11, Lewis structure for ethanol, which is CH3, CH2, OH. So this one is kind of straightforward. So before even calculating the number of valence electrons, we can kind of guess that since it was written this way, that this first carbon has the 3 hydrogens, the second carbon has the 2, which is bonded to an oxygen and another hydrogen at the end to form an alcohol group. So now let's see the total valence electrons. So there are 2 carbons, each with 4 valence electrons. And for hydrogen, there is 1 valence electron. And there are 1, 2, 3, 4, 5, 6 hydrogens. And 1 oxygen that has 6 valence electrons. So this gives us 20 in total. And if we count out all the bonds, with each bond containing 2 electrons being shared, we have 8 bonds drawn. So 8 times 2 is 16. And the remaining 4 electrons will be drawn on the oxygen, since oxygen does not have a full shell yet. So this is the Lewis structure for ethanol, and the junior tutors said the same thing. So this solution is correct. Question 12 is to draw the Lewis structure for PF5, so phosphorus pentafluoride. What is the smallest or ideal bond angle in the structure? So first, let's find the total number of valence electrons. So phosphorus has 5, and fluorine has 7, and there are 5 fluorine atoms. So 35 plus 5 gives us 40 electrons in total, or the valence electrons. So let's draw phosphorus in the middle, and then we'll symmetrically draw all the fluorine atoms with single bonds, and I'll also fill in all of the lone pairs that are on each fluorine. So if we count out the number of electrons I've drawn so far, with each bond containing 2 electrons, we already have our 40 shown in the structure. So for the second part, what is the smallest bond angle? It helps if we find out its molecular and electron geometry. So our central atom, which is phosphorus, has 0 lone pairs. and it has 5 bond pairs, which are all of the fluorine atoms. So if we look at a VSEPR table, there are 5 total domains, 5 bonded atoms, 0 lone pairs. This gives us a molecular shape that is trigonal bipyramid or bipyramidal. Its hybridization is sp3d. And for the bond angles, it's 90 degrees. So this is the smallest bond angle. And the junior tutor said phosphorus pentafluoride has a total of 40 valence electrons. And they've got the remaining Lewis structure. And the electron pair geometry and molecular geometry is trigonal bipyramidal, which has a bond angles of 120 between the equatorial atoms and 90 between the axial and equatorial atoms. Therefore, the smallest FPF bond angle in the structure is that of the axial and equatorial atoms, which is 90 degrees. Okay, so the solution is correct. Okay, so question number 13. Distinguish between the terms electronegativity versus electron affinity, covalent bond versus ionic bond, pure covalent bond versus polar covalent. Characterize the types of bonds in terms of electronegativity difference, and energetically, why do ionic and covalent bonds form? So first, electronegativity is the tendency of an atom to attract electrons, and electron affinity is the energy change when an electron is added to a neutral atom or molecule. So this is the definitions of the two terms. And now for the second part of the question, we need to distinguish covalent versus ionic bonds. So first, I'll just define all the different bonds. So you can have a nonpolar covalent bonds, which is when 2 atoms have equal or similar electronegativity values. And in terms of electronegativity difference, for nonpolar covalent bonds, the difference is around, or the range can range from 0 to 0.5. So some examples of nonpolar covalent bonds are like diatomic molecules such as nitrogen-nitrogen, so N2, or even the carbon-hydrogen bond, which only has an electronegativity difference of 0.4. So this is nonpolar covalent, and we can have polar covalent, which is when the 2 atoms have dissimilar electronegativity values, So the change in electronegativity for polar covalent bonds usually around 0.5 to 1.69. So some examples of polar covalent bonds would be like carbon and oxygen, or like hydrogen and oxygen, etc. And the main difference between covalent and ionic bonds is that covalent bonds are between two nonmetals, and it involves the sharing of electrons. Nonmetals. In the case of an ionic bond, this is between a metal and a nonmetal. So the minute you see a metal involved in the bonding, you already know that it is an ionic bond. And in terms of the electronegativity difference in an ionic bond, it is typically greater than 1.7. So an example would be like potassium fluoride. So for ionic bonds, this is when a metal would give one of its electrons to a nonmetal. So you're not sharing the electrons to form the bond. It is when, let's say we had a sodium ion that has one valence electron, and we have a chlorine that has 7. The sodium donates its electron to the chlorine, and this is how sodium chloride is formed. So sodium has a positive charge and the chlorine has a negative charge, and this is what forms the ionic bond. So the junior tutor said that the tendency of an atom and a molecule by which it attracts electrons towards itself in the case of a covalent bond is termed electronegativity. The measurement of electronegativity is not possible directly and has to be calculated from other atomic and molecular properties, while the energy change when an electron is added to a neutral atom or molecule in its gaseous state is known as the electron affinity. Tendency of an atom and a molecule by which it attracts the electrons towards itself in the case of a covalent bond is termed electronegativity. Energy change when an electron is added is electron affinity. Covalent versus ionic. So they show the sharing of electrons between atoms, and ionic is formed through electrostatic attraction between the metal and the nonmetal. Okay, and then pure covalent versus polar. This is dependent on the difference in electronegativities. And the formation of two bonds takes place when the electronegativity difference among the atoms exceeds 1.7, it's ionic, and if it's less, then it's 1.7. Okay, so I'll also add the ranges for nonpolar and polar covalent. So this solution is correct. Also, the electronegativity difference, or for nonpolar covalent bonds, ranges from 0 to 0.5. Let's say 0.4. For polar covalent bonds, 0.5 to 1.69. Okay, so I think we have time for one more quick question. What is the formation equation for, this is acetic acid. Let's do that first. So when we have a formation equation, this is just when we have our elements coming together to form the final product. So carbon is in its solid state. Hydrogen is a gas, and it would be in its elemental state, which is H2. And similarly, we have oxygen, which is in its elemental state as well, which is O2. And this forms acetic acid. And we just need to balance the equation now. So we have 2 carbons and 4 hydrogens on our product side. So I'm going to put a coefficient of 2 and O2. So this is the balanced formation equation for acetic acid. So now for NaHS, we start off with our sodium, which would be solid. Hydrogen again is in its diatomic form. And sulfur is just a gas. If we were to balance this equation, we need to put a coefficient of 2 in front, just so that we can balance out the hydrogens. And now we just need to put another coefficient of 2 in front of sodium so that everything is balanced. Now let's see what the junior tutor said. Since acetic acid has carbon, hydrogen, and oxygen, unbalanced formation equation is this. And when they balanced it, they had the 2 coefficient in front of carbon and hydrogen. And for NaHS, they have the unbalanced formation equation. And when they balanced it, they put the 2 in front of the sodium and got the same thing. Oh yeah, so the sulfur should also have a coefficient of 2. Okay, so now everything is balanced and this solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you enjoyed today's video, you can give it a thumbs up and a comment, and you can share it with your friends and classmates if they needed any help with chemistry. And if you wanted to submit a question of your own, then check out the links in the description. This has been Donna from OneClass, and I hope to see you soon. Bye.